Okay.
Okay, but anyway, for example, the set message to Риера,
Okay, thank you. So, let me begin by recalling two of the results I proved yesterday. Result number 0 was the computation of the cohomology of the classifying space of mu p, the group of p-th roots of unity, with zp coefficients, and this turns out to be isomorphic to z mod p in all dimensions. And second, if X is a manifold and mu p acts on M, then I prove that case cohomology, equivariant cohomology of X with coefficients in Z mod P is isomorphic to the. Sorry? Yeah, sorry. Sorry. Yeah. Then this coincides with the equivariant cohomology of the fixed point set as soon as K is bigger than the dimension of X plus 2. Bigger or equal than, okay? Now, statement 0 and QNet imply the following: the dimension of the case equivariant cohomology of the fixed point set. So this is a vector space over Z mod P, and that's the sense in which I talk about its dimension. It is equal to the sum of the Betti numbers of the fixed point set with Z mod P coefficients as soon as K is bigger or equal than the dimension of let's say of X, which of course is bigger or equal than the dimension of the fixed point set. Okay? Well, now let me now state a bound on the dimension of the equivariant cohomology of X. Okay? Namely, the dimension of the equivariant cohomology sorry? Yeah, this is mu p, sorry. Yeah. So this dimension is at most the sum of the Betti numbers of X with ZP coefficients. ZP coefficients. Okay, and this holds for any K. Okay. And the proof follows from the third spectral sequence. Which recall has second page with these entries, and this converges to Okay, but now what we need is to bound the dimension of this guy in terms of the dimension of the cohomology of J. Okay. Okay. The subtle point here is the following. If mu p acts trivially on the homology of X with Z mod p coefficients, then this local system is trivial. So we can replace this cohomology with coefficients in a local system with cohomology with coefficients in the group Hj of X. Okay? And in that case, you simply apply this fact and the universal coefficient theorem or whatever to conclude this inequality. However, in general, we don't assume that the action is trivial on cohomology, so we need a general fact about homology of local systems on the classifying space, and this will be the next lemma. Okay, so this is, suppose that V is a vector space over Z mod P, and suppose that mu P acts linearly on V. Let this calligraphic V denote the associated local system over the classifying space mu P. Okay? Then the statement is that the dimension of the classifying space with coefficients in that local system in any degree is bounded above by the dimension of V. Okay? So I guess it's clear that if we prove this lemma, then this inequality will be justified.
Just the point that we are working with EG and
so we're going to apply this to this for any G.
Yeah, so replace, it's important that we are working with the cyclical theorem.
Oh yes. What I'm going to, the proof I'm going to give works also for replacing mu p by a finite p group, if you want. If this is your, well, what is crucial is that the characteristic of the field is the same as the prime p. That's crucial. Otherwise, this is in general false. Okay.
And on the other hand, it is important that this kind of system,
you will see that the argument applies in a much wider situation. I'm just stating the lemma this way because this is precisely the statement I'm using. But I mean, the idea is the following. First, I claim that there exists a filtration of V by vector spaces so that each Vi is a mu p invariant vector subspace of V, and the action of, so mu p has an induced action of each quotient of Vi by its predecessor, and this action is trivial. Okay? And of course, I define V minus 1 to V0. No, V0, sorry. Okay, so let's prove the claim. Let's prove, for example, that the subspace of fixed vectors is non-trivial. Okay, so of course, let me assume that the dimension of V is at, yes? What? Sorry?
What coefficients in state?
Always, you mean this?
Yes.
Z mod P.
But there is new dimension of yeah.
Here, this is a local system. So I'm talking with cohomology with coefficients in a local system. This is a twisted version of cohomology. Okay, you can understand it also in terms of sheaf cohomology. Okay, so a local system is a particular case of sheaf, and this is the cohomology of this sheaf over this space. Okay, let me assume that the dimension of V is bigger or equal than 1. Then the cardinal of V minus the space of vectors fixed by mu P is divisible by P. Okay, because if you take any vector which is not contained here, then its orbit contains P elements. Again, the same basic fact that I used yesterday. If you have a subgroup of mu P, it is either the trivial subgroup or the total subgroup. Okay, so we have this, and since, of course, this is the cardinal of V minus the cardinal of V mu P, conclusion, P divides the cardinal of V mu P, because P certainly divides the cardinal of V, and then this implies that the dimension of V mu P is at least 1. Okay? And now set V1 to be equal to the subspace of fixed vectors, and repeat the argument. Replacing V by V divided by V1. Okay? Is that clear? Well, I'm not writing things in a perfect way. You could think of this argument as applying induction on the dimension of V. Okay? Let's apply the induction on the dimension of V. If the dimension of V is equal to 1, then this argument proves that the action of mu P is trivial. Okay? Otherwise, assume now that the dimension of V is bigger than 1 and that the statement is true for vector spaces of lower dimension. Okay? Now I've proved that V1 defined in this way is non-zero. Now I apply the induction hypothesis to this quotient, and then I get a filtration of this quotient, and I lift this filtration to a filtration of V by taking the pre-images through the quotient from V to this quotient. Is that clear? Okay. Now this proves this, and now so the claim is proved, and to prove the lemma, we again use induction. Namely, I prove that the dimension, oh, sorry, that's not a very good idea. I prove that the dimension of this homology, so now each of these spaces in the filtration gives me a local system, okay, and I prove that this is at most the dimension of VL, okay, and I use it induction on L, okay, so the case L equal 1 follows from change of coefficients, if you want, because the action of mu p on V1 is trivial. Okay? And now, assuming that L is bigger or equal than 2, and assuming that this formula is true for L minus 1, then we have this a short exact sequence of local systems, which you can consider to be sheaves, okay, and then take the cohomology long exact sequence associated to this short exact sequence of sheaves, and use the bounds, these bounds on the for L minus 1, and use the fact that the action of mu p here is trivial. Okay, so again, you can identify the cohomology with coefficients in this local system with the cohomology with coefficients in the vector space with straight V's here. Okay, okay. So now I have proved this lemma, which implies statement 3, and now we can combine statements 1, 2, and 3 and obtain the following theorem. So this is a theorem of Smith. It was proved in the 30s using different techniques. The techniques that I am using are due to Borel, and they were introduced in the 60s. This theorem is from the 30s. It says the following, that if X is a manifold supporting an action of mu p, okay, let us assume that it is well, not necessarily close, I mean, but assume that the sum of the Betti numbers is finite. Then, we didn't use what? Compactness. That's right. No, it's true. Did I assume that X was compact in the previous? I mean, the only thing we need for these arguments to work is that the total cohomology is finite. Total cohomology with coefficients in Z mod P.
So the general
Not necessarily. I will try to be careful to specify when it is necessary. But for example, I'm going to use this sort of results on contractible manifolds in some situations, okay? Although the theorems I will finally prove about restrictions of finite group actions will most of the times apply only to closed manifolds. So compact and without boundary. Okay? But this is true in more generality. Okay? And the statement is that this is bounded by the sum of the Betti numbers of the fixed point set is bounded by the sum of the Betti numbers of the ambient manifold. Okay? Let me give an example of application of this theorem. Suppose that X is say, compact, oriented and connected surface. Okay? And suppose that the cyclic group of two elements acts on S, reversing the orientation. Okay? Now, in that case, you can prove that the fixed point set is the disjoint union of a collection of circles. Okay? So this follows, for example, from the argument on linearizing actions through the exponential map with respect to an invariant metric. The argument that I sketched yesterday to prove, for example, that the fixed point set is a submanifold. Okay? This same argument combined with the assumption that the non-trivial element in mu2 reverses the orientation implies that the fixed point set has necessarily dimension 1. Okay? It is also compact, so it is a disjoint union of circles. And now, yes? Not yet. No. I'm going to use it now to bound the number of components. Okay? By Smith's theorem, the number of connected components of the fixed point set can be bound as follows. So each connected component is a circle, and hence the sum of its Betti numbers is 2. Okay? So let's put a 2 multiplying here for the sum of the Betti numbers of the circle. And now this is bounded above by the sum of the Betti numbers of S, okay, which is 2 plus 2G. Okay, so G is the genus of S. Okay, so we have this bound. So the number of circles is at most 1 plus G. And this is a sharp inequality. Okay? So if you draw a surface this way, and you consider the involution that, I guess it's clear what I mean, that reverses the surface, you have these collections of circles that are fixed, okay? And you get the number of fixed circles is the number of holes plus 1, okay? which is exactly this bound. Now, there's an interesting particular case of this situation, which comes from algebraic geometry, and I think it's say it again. That it reverses the orientation. Yeah. Otherwise, you could have isolated fixed points. I'm interested on the situation where. Yeah. I mean, if you know that it reverses orientation, then of course you can obtain meaningful statements without assuming that it reverses orientation. But I'm interested in this case because I'm not going to apply it to the Galois action of.
But why can't you have an isolated point in this case?
Okay. This has to do with the linearization statement. Okay. Suppose that you have an isolated fixed point. Okay. In your surface. Now you look at the infinitesimal action at the tangent space here. Since it, exactly. And this exactly, yeah. Yeah. I mean the infinitesimal action has to reverse the orientation and hence has to have a fixed line, and now this line is tangent to a connected component of the fixed point set, which is necessarily a circle. Okay. Now there is one example. One particular case. Which is the following. Suppose that P is a polynomial in 3 variables with real coefficients of degree delta. Okay, then consider it's zero set, but in the complex projective plane. Okay. Now, if S is smooth, then then it is a compact connected Riemann surface of genus of this genus. Okay, and now, assuming smoothness, consider the action of mu2 on S that conjugates the homogeneous coordinates, and well, it's an easy exercise to prove that the fixed point set are precisely the solutions of the polynomial equation in RP2. Okay, and now if we combine this with this bound here, the conclusion is that this real curve, let's call it C, has at most this number of connected components. Okay. So, for example, if we take a cubic equation, if you take a cubic equation, you know that with real coefficients, you typically get either such a picture or such a picture, okay? Provided you get real points, okay? But you will never get three connected components, okay? And this is a consequence of this bound here. Okay, so this is an example of application of finite transformation groups to real algebraic geometry. And this was probably first observed by Rochlin, the importance of using these statements in the context of real algebraic geometry, and this was very much exploited by Arnold. Okay, so this is if you think in case of conics, what this is telling you is that a real conic has at most one connected component. But of course, this is in the real projective plane. If you look at standard hyperbola, you will see two connected components, but it is because you typically draw things in the affine plane and not in the projective plane. Okay, in the projective plane, all non-empty real conics are connected. Okay, so this was one of the theorems, classical theorems of Smith. Let me now prove another classical theorem of Smith. Let me say that the space is Z mod P a cyclic if its cohomology with coefficients in Z mod P coincides with the cohomology of the point. Okay, so for example, if X is contractible. But this is certainly a weaker condition. Okay. Now, a simple observation is the following. So this is, by the way, 0.5, I think. Yeah. If you have an action of mu p on a Z mod p cyclic manifold, then its equivariant cohomology coincides with the equivariant cohomology of the point, with the cohomology of the classifying space for mu p. Okay, so this is of course, if X is contractible, that's immediate, because you know that the Borel construction fibers over the classifying space, and the fibers are copies of X. So if X is contractible, the projection to B mu p is a homotopy equivalence. This need not be the case in general for Z mod p cyclic spaces. Okay, but precisely because this is precisely because we are working with Z mod p coefficients, we don't see anything but the cyclicity of X. And a rigorous argument would be to apply Serre's spectral sequence. Okay. Okay, so the condition that X is Z mod p cyclic means that here in all rows above the bottom one, you have zeros, okay? And here you have, of course, copies of Z mod P, so the spectral sequence degenerates in the second page, and this gives you the isomorphism, okay? Now, if we combine 1, 2, and 5, we get the following theorem of Smith. If X is a Z mod P acyclic manifold, and mu P acts on X, then the fixed point set is again Z mod P acyclic. In particular, the fixed point set is non-empty and connected. Okay. An important remark is that I'm using here the fact that X is a manifold, which definitely means for us that it is finite dimensional. Okay? Because otherwise, you could take the action of Z mod P on S infinity. S infinity is contractible, so it's certainly Z mod P acyclic, and the action of mu P on S infinity that, for example, appears in the universal bundle construction is free. Okay? I mean, you have a free action of mu P on S infinity. Okay.
Why it's not an equivalent wave statement, it's only one wave,
Yes, absolutely.
How can we justify
Okay.
something similar about homology of
Okay. You assume that X is Z mod P acyclic, and then you conclude that its cohomology coincides with this. Okay. Now, you use the fact that in high degrees, the equivariant cohomology coincides with the equivariant cohomology of X coincides with the equivariant cohomology of the fixed point set. Okay? Now, the equivariant cohomology of the fixed point set you can compute using QNet. Okay? And since the equivariant cohomology of the fixed point set coincides with the equivariant cohomology of the classifying space, by QNet, not by the converse of this, but by QNet, you conclude that the fixed point set is Z mod P acyclic. Okay, but because what you know is that this is isomorphic to the to this tensor product. Okay, and so this tells you that the dimension, this gives you a relation between the dimension of each piece in the cohomology here with these ones, and recall that each piece of this cohomology has dimension 1, so the relation is very easy. Yeah? Okay, and finally, this theorem can be automatically extended to actions not only of Z mod P, but of any finite P group. Okay? Okay, and now first recall, a finite P group is a group whose cardinal is a power of P. Okay. And if you have a finite P group, you always have a filtration of the group, okay, by normal subgroups, a normal filtration, such that the consecutive quotients are isomorphic to Z mod P. Okay? And again, sorry? Yeah. Okay. How does one prove this? It's basically the same argument that I used in my claim about local systems. Okay? You consider the action of G on itself by conjugation. Okay? Now, what you know is that orbits of this action have cardinal which is a power of P. There is certainly one orbit whose cardinal is not divisible by P, which is the orbit of the identity, because identity commutes with all the elements. On the other hand, the total cardinal of G, assuming that G is non-trivial, is a power of P, so it's divisible by P. Okay? This implies that the center of G has to be non-trivial. Namely, that there must be elements which commute with all elements of G and which are not equal to the identity. Okay? So now what you do is the following. You define G1 to be the center of G, and then, again, you quotient by G1 and apply the argument recursively. Okay? So semi-argument as for local system.
Could you please give an example of, is it a cyclic manifold which is not acyclic?
It's not so hard to construct one. So you do the following. You first construct a CW complex which has this property. Okay? So how can you construct one? So for example, it's easy to construct a CW complex which is connected, so which is isomorphic to Z, and which has yeah, I can give you an example. Yeah, a very easy example. So RP2, for example, this is a very stupid example. RP2 is Z mod 3 acyclic. Okay, because the cohomology of RP2 in positive dimensions is of exponent 2. Okay, but I mean this is a silly example. A more general way to construct is you first construct a CW complex, okay, by adding a finite number of cells. This is in general easy, okay, because it's very easy in terms of the attaching maps to control the cohomology, okay, and then you embed this in an Euclidean space, and you take a retract neighborhood and you get an open manifold, which is Z mod P acyclic for any P you have chosen a priori. But, by the way, it is an interesting fact that this theorem is sharp in the following sense. I mean, there are concrete examples in which you have a Z mod P action on not in any ZP acyclic manifolds, but on Rn or on a disk, okay, whose fixed point set has an arbitrary homotopy type, provided this homotopy type is ZP acyclic. Okay, so you can't obtain anything stronger than that for general ZP actions. Okay, so let's go back to the corollary. So we have, in general, for any finite P group, such a filtration, and now you obtain the corollary from the theorem using induction. Okay, because you have that X is Z mod P acyclic, and then this implies that the points fixed by G1 is a Z mod P acyclic space. Okay, now here acts G2 mod G1. Okay, which is isomorphic to Z mod P. So again, you can apply the theorem, and this, which of course coincides with G2, is Z mod P acyclic, etc. Until you reach the conclusion that XG is Z mod P acyclic. Okay? Okay. Well, so now let me begin to obtain some fruits out of this effort. I will first prove a general theorem by Borel that puts restrictions on finite group actions on certain manifolds. Then I will see that this applies in particular to closed hyperbolic manifolds. And this will be our first generalization of the theorem for actions on surfaces. Okay? So, first some preliminaries. So this is going to be suppose that X is a connected. No, let me first recall one definition. Let gamma be a group. Then out of gamma denotes the group of automorphisms of gamma. And inside here you have a normal subgroup which is called in of gamma, which is the inner automorphisms. Everybody knows what this means. I mean, these are automorphisms given by conjugation. Okay, so this is an inner automorphism. Okay. And now the outer automorphism group is defined to be the quotient. Okay? Now suppose that G is a connected, say, manifold, although this works for locally are connected spaces, and G acts on X. Okay. Now let's fix a base point on X and define gamma to be the fundamental group. Okay. Now the action of G on X needs not define an action of G on gamma, because a priori there is no reason why the base point should be fixed by G. If the base point is fixed by G, certainly you get a well-defined action. However, in general, what you get is a well-defined morphism from G to out of gamma. Okay? So how is this defined? Take any G. And now we have to send this to an outer automorphism. An outer automorphism is an automorphism defined up to inner automorphism. Okay? So I'm going to send this to the class of some automorphism. And this automorphism is going to be the following. Suppose that gamma, little gamma, or let's call it, suppose that rho is a loop beginning and ending at x0, representing a certain element of gamma. Okay? Now, this is sent to the class of this concatenation. Well, if you want, let's be completely precise. Let's draw it this way. And now psi is a path from x0 to gx0. Okay? So what we are doing is the following. So this is x0, this is the path rho, okay, and now this is going to be the composition. Recall that phi g denotes the diffeomorphism of X given by the action of G. And now what we have, we take a path psi going from x0 to gx0, okay, and now we declare the image of this element of the fundamental group to be this concatenation. We go this way, then this way, and then back to x0. Okay? Now, this is not a well-defined element of the fundamental group because psi is in general not unique at two homotopy. However, the ambiguity lies entirely in the inner automorphism group. Okay? Well, so this is the definition of this action. Not on the other hand, I didn't say this explicitly, but I guess it is rather obvious that if you have a group action on X, then there is a well-defined action on homology and cohomology. Here we don't have any problem because we don't use any base point. Okay?
So what does this mean? For each j, we choose psi between x0 and j0.
For each G.
This choice defines here an automorphism, and
Yes.
the class is the automorphism doesn't depend on it.
Well, it doesn't even define an automorphism, to be clear. No, what am I saying? No. No, it does define an automorphism, only that it is not well defined because it depends on the choice of psi. That's it, yes.
I mean, once you choose psi, you get an automorphism, and then check that when you change it, just
Exactly, yeah. The thing is that if you take two different xi's, they will differ by an element of the fundamental group, okay? And it is conjugation by this element that tells you how the two possible automorphisms differ. Okay, so now, so Borel's theorem says the following. So this is a theorem from end of the 60s. Suppose that X is now it is a closed, orientable, a spherical manifold. So a spherical means that its universal cover is contractible. I mean, in particular, it is connected. Now, let gamma be the fundamental group of X with respect to any base point. Suppose that the center of gamma, so this that denotes center, is finite. Then the conclusion is that if G finite acts on X effectively and smoothly, the induced map from G to out of gamma is injective. Okay, let's prove this theorem. So let's prove the statement by contradiction. Suppose that G is non-trivial, and let's give a name to this map. Let's call it psi. Okay. Now let Y be the universal cover of X. Since by assumption X is a spherical, Y is contractible. In particular, it is Z mod P acyclic. Okay. Let's take now a lift F of phi G. Okay, so phi G is the diffeomorphism from X to X sending given by the action of G. Okay. Now, precisely because psi G is equal to 1, there exists some chi in gamma such that f of gamma x is equal to chi gamma chi minus 1 acting on f of x. So yes. Maybe I should say y, little y. And this is true for any y in the universal cover and any gamma in big gamma. Okay? So the existence of this chi is a consequence of the assumption that little g is mapped to the kernel. So it is a I mean, the chi is well defined once you have chosen the lift f. Okay? Good. So now if we define h again from y to y this way, then and h of gamma y is gamma h of y. Okay, this is a consequence of that formula there. If you move this chi to the other side, you get exactly that expression. Okay, so now h is gamma equivariant. Okay, good. Now h is again a lift of phi g. Okay, so now I forgot to say here one thing. I said let's take a non-trivial element in the kernel of psi. We can assume, replacing g by a power of g, that the order of g is a prime number. Okay? You look at the order of g, you take one prime divisor, and then you raise g to its order divided by p. Okay? So replacing g by g to some m, we can assume that the order of g is prime. Okay? Good. Now, since phi g to the p, I mean the composition of phi g with itself p times, is the identity in X, okay, so if you compose H with itself p times, you get a lift of phi g composed with itself p times, which is identity, and hence H to the p consists of making some fixed element of gamma act on y. Okay? Now, the equivariance implies that zeta belongs to the center of gamma, okay? I mean, if the operation of multiplying by zeta is equivariant, namely commute with multiplication with any other element of gamma, then zeta certainly has to be central, okay? Because gamma acts effectively. In fact, it acts freely on Y, okay? Now, by assumption, this is finite. Okay, so this means that a certain power of H is the identity on Y. Namely, H has finite order.
What is this part?
This. Yeah. Since zeta gamma is finite, the order of the lift H is finite. Okay? Now, the order of H is going to be P to the E times Q, where P doesn't divide Q. Okay? And E is bigger or equal than 1. Okay? If the order of H was not divisible by P, then we would conclude that the order of phi G were not divisible by P, which would be a contradiction by our assumption that G has order P. Okay? Now, replacing G by G to the Q, and H by H to the Q, we have that the order of H now is P to the E, and H lifts phi G. Okay? Good. Now, H is I mean, the action of H is a diffeomorphism of Y, which has finite order, which is a power of P. Okay? So since, let F be the fixed point, since Y is contractible, it is Z mod P acyclic. By Smith's theorem, F is Z mod P acyclic. Okay, we are near the end. Because H is equivariant, F is gamma invariant. It's preserved by gamma. Okay? And of course, gamma acts freely on F because it acts freely on the entire Y. Now, using that, the inclusion of f inside Y induces an isomorphism in cohomology with coefficient in Z mod P and shares a spectral sequence, and of course this inclusion is gamma equivariant. What we get is that the gamma equivariant cohomology of F with Z mod P coefficients is isomorphic to the gamma equivariant cohomology of Y with Z mod P coefficients. Okay? Now, remember, when a group acts freely on a manifold, the equivariant cohomology is isomorphic to the cohomology of the quotient. And gamma acts freely both on F and Y. So this is isomorphic to the cohomology of X with coefficients in Z mod P. And this is isomorphic to the cohomology of F mod gamma. Okay? Oh, sorry, non-equivariant. Okay, now, X is a closed connected orientable manifold. So you can read the dimension of X from the cohomology in Z mod P coefficients. Namely, you look at the highest degree in cohomology where you get something non-zero. And this is telling you the dimension of X. But F mod gamma is also a smooth manifold. Okay? Because F is a smooth manifold and gamma acts freely and discretely on F. Okay? So now this implies that the dimension of F mod gamma has to be at least the dimension of X. But F is a submanifold of Y. Y has the same dimension of X. The conclusion is that F has to be the entire Y. Let n be the dimension of X. Now, this is non-zero, okay? Since F since F mod gamma is a manifold, the fact that this is non-zero and that it coincides with Hn, sorry, let me write it here. So Hn of F mod gamma with coefficients in Z mod P is non-zero, okay? And now the conclusion is that the dimension of F mod gamma is at least the dimension of X. Okay? The dimension of X is the same as the dimension of Y. And this is the same as the dimension of F. Okay? F is a set of points in Y fixed by the action of H, which is an element, diffeomorphism of finite order. So F is a submanifold of Y, and if it has dimension bigger or equal than the dimension of Y, since Y is connected, F is equal to Y. But F is a set of points fixed by H, so H is the identity, and now this implies that phi g is the identity, which is a contradiction. Okay? Well, so this is an abstract theorem, and let me now give you an example of a concrete application. Suppose that M is a closed connected manifold, closed connected and oriented manifold. And now we assume that M supports a hyperbolic metric. Okay? In particular, this implies that X is spherical. By Hadamar's theorem, I mean, the universal cover has to be, in fact, isometric to hyperbolic space. Now, the conclusion is that there exists some constant C such that if a finite group acts on X effectively, then G has at most C elements. Okay? Let me insist that I'm not assuming that this action is compatible with the hyperbolic metric. Okay? I mean, I assume that M supports a hyperbolic metric, then I forget the hyperbolic metric, and I consider arbitrary, smooth, finite group actions. Okay? This corollary, by the way, generalizes to arbitrary dimensions the statement for actions of groups on surfaces of genus 2 or more, because these surfaces support hyperbolic metrics. Okay? Now, to prove the corollary, I have to check the hypothesis in Borel's theorem. Sorry? Some constant, yeah. It is involved here. Well, I mean, C exists independently of G. So what the statement tells you is that there is a uniform bound on the size of the finite groups that act on M. For example, a consequence, M does not support any smooth action of the circle. Because if you had an action, a smooth effective action of the circle, you could restrict it to the groups of nth groups of unity, and taking N big enough, you would get a contradiction with that. Okay, so to prove the corollary, let gamma be the fundamental group. We need to check two things. First, yes, that the center of gamma is finite. And second, that the outer automorphism group of gamma is finite. Okay, then applying Borel's theorem, we obtain that the size, taking C equal to the size of out of gamma, you get the bound. Right? Now, how does one prove that? Proof of one. So gamma is a fundamental group of a hyperbolic manifold, of a closed hyperbolic manifold. Then you can identify gamma with a lattice inside ON1. Okay? A lattice is a discrete subgroup with finite covolume, in particular if the quotient of the hyperbolic space by gamma is compact, then certainly gamma is, if it's discrete, then it is a lattice. Now, by Borel's density theorem, gamma is of ON1. ON1 is the isometry group of HN. Well, I should put a plus here because this has, it is a subgroup of ON1 plus is the subgroup of index 2. Sorry? It suffices that it has finite covolume. Covolume, yeah, that the quotient has finite. You project the Haar measure here to the quotient and you want it to have finite volume. Now, by Borel's density theorem, gamma is a risky dense. And this implies that the center of gamma is contained in the center of the group. Okay, because the center of gamma are the elements of gamma that commute with all the elements of gamma. But if you have an element of gamma that commutes with all the elements of gamma, since gamma is a risky dense, this element commutes with all elements of the group. Okay? So you have this inclusion. But this is finite. Okay, that's easy to... It's easy to compute the center of this group. It has maybe 4 elements, I guess. Okay, let's finish by proving 2. Well, in fact, now I remember. For the argument, I distinguish the case dimension 2 and dimension 3 and higher, okay? Well, so it's a sui generis generalization, huh? Okay? So, let's say that if the dimension of x, I'm all the time confusing m and x, sorry. This should be an x. So, if dim of x is equal to 2, then, okay, we proved it yesterday. So we assume that the dimension is bigger or equal than 3. Okay? Now, prove that the out of gamma is finite. Let F be an automorphism of gamma. Okay? Now, this induces a homotopy equivalence of the classifying space of gamma. Okay? Very fast. How does this work? You have the universal principal gamma bundle. Okay? Gamma acts here on the right. Now you twist the action of gamma on E gamma using the automorphism F. Okay? So you define if P belongs to E gamma and little gamma is an element of gamma, you define the action, let's denote this action with a star, to be the usual action of F gamma. So this dot is the usual action of gamma on each E gamma. Okay? So this defines a new action of gamma on E gamma. Okay? So this guy, which was initially a principal gamma bundle, gets transformed into another principal gamma bundle. But now you use the fact that this classifies bundles. Okay. Okay, so this justifies the fact that F, I mean, what I'm proving here is the naturality of the classifying space construction, okay? If you, if you have a morphism of groups, any morphism of groups induces a map, continuous map between the classifying spaces, okay? Now, this is homotopy equivalent to the manifold X, okay? Because the universal cover of X, by assumption, because it is hyperbolic, is spherical, it's contractible. Okay, so this is a particular example of classifying space. Okay, so now we get a homotopy equivalence of X with itself, and now we use Mostow rigidity. So, sorry, let me first previously fix a hyperbolic metric zeta on X. And now by Mostow rigidity, phi is homotopic to an element of the isometry group of M with a hyperbolic metric zeta. Okay? So here, of course, I'm using that the dimension of X is at least 3. Otherwise, Mostow rigidity doesn't apply. Well, this implies, I'm almost finished. Sorry? Yeah, sorry. On the other hand, I mean, so phi is a map from X to X, which is a homotopy equivalence, and so it defines an element out of gamma, and it coincides with the class of F. Now, it follows that this morphism is surjective. Okay? Again, to prove the surjectivity, you take any element here. You lift it to an automorphism, F. You construct phi out of F, and then you apply Mostow rigidity to replace phi by an isometry which is homotopic to phi. Okay? And then you get some isometry that goes to the element you have chosen here. Now we are almost finished, because by Myers-Steenrod theorem, this is a compact Lie group. The classical theorem of Myers and Steenrod. It applies to general Riemannian metrics on closed manifold. You have a closed manifold, you take any Riemannian metric, its isometry group is a compact Lie group. Sorry? No, Meyer-Steenrod is true for not necessarily hyperbolic metrics, okay? Now this implies that this map, let's call it psi, is locally constant, and hence, and since this is compact, it has finitely many connected components, so out is finite. And this finishes the proof, okay? So this is subjunctive. Okay, so as I said, this extends to higher dimensions in the case of genus 2. So tomorrow I will state two theorems, one applying to so-called hypertoral manifolds, which generalize both cases, the surface of genus 1 or higher, in fact. And I will also give a theorem about actions of manifolds with non-zero Euler characteristic, which generalizes the case of genus 0 or genus 2 or higher. Okay. Yes, I'm using it, yes. I'm talking about the isometry group of a Riemannian metric. If you take on the sphere, for example, the round metric, the isometry group is the orthogonal group. Sorry? Where I use what?
The dimension assumption, greater than 3.
In Morstov rigidity. So Morstov rigidity is not true in dimension 2. Because in dimension 2 you have moduli of hyperbolic metrics.